I brought it, but then
Wait a minute.
what the fuck? Oh, I where is it looking at?
Remember when we first did the op-amp portion, we either select inverting or non-inverting input, and then we went out and tried to drive 32 ohm, and that didn't work because the current is not enough to drive the load, which is very small, which means that the op-amp cannot deliver the current. And that's why now we are now using the op-amp as a preamp before the amp. So this amplifier is a single stage, which we have just learned, BJT transistor. And again, based on your metric number, whether your second digit matrix numbers ending with or rather is odd or even, we then select whether we are going to use PNP or NPN. But whether is it an NPN or PNP, having a supply voltage that is plus and minus VCC, again depending on the values that you are supposed to use for the last two digits, alright? This may be, let's say, 2 point something volt plus and 2 point something volt minus, and therefore this point, which is the DC voltage output, should be what value? What? Anyone? Okay, so suppose this is, let's say, 2 volt here, minus 2 volt here, and this point should be 0. Why you want it to be 0? So that if this capacitor is not there, then this is 0, this is 0, there's no current going through this resistive load. That means without any signal, there is no power loss to the load. So the load only draws current when the voltage at VE starts to move with respect to ground, and therefore there will be current flowing. So the reason for this cap, okay, the reason for this cap is that if this voltage VE is not 0 volt, then even though this is not 0 volt, there will be no DC current flowing through the load. That's the purpose of this cap, and this cap is known as it's called a DC blocking capacitor or AC coupling capacitor, right? So it couple AC but block DC. Why you block DC? Because you don't want the DC to have a permanent current flowing through the resistor, which will draw current from the power supply, which will deplete your battery. Okay, so that's the purpose of it. So if we again look at this, so now if we connect this point to ground, the minus VCC, we connect it to ground, then what should this voltage be at VE? No, it will be half the supply voltage. And because it's half the supply voltage, we need this cap. Because the other end of this resistor is connected to ground. So we cannot have, when there's no signal, there's a permanent current flowing through the load, because that will deplete the battery. You understand the concept now? So if we have a load, okay, if we don't want current to flow here, then the voltage here, oops, sorry, then the voltage at this point and the voltage at this point must be the same, so that there's no current flowing, right? So if there's a voltage at this point, that's where this DC decoupling cap is supposed to be at, so that there's no DC current flowing. Unless there's AC, then the AC will flow through. So that depends on this amplifier. If the amplifier is connected to ground and VCC, then we need this point to be VCC over 2. Why VCC over 2? Because any signal that goes through this amplifier, for instance, okay, so that the output here, if we have a signal here, we want this signal to swing, and this signal swing, at the most it can go is VCC, at the least it can go is ground, alright? Correct? And therefore this signal must be able to transverse from VCC to ground, so that the most optimum point for the DC voltage will be half VCC, because then the signal can swing in both ways. Remember when we did the op-amp, we say that if there's a DC voltage at the output, one of the swing will be depleted, right? Same thing here. We want to maximize it by having the DC voltage at the center, right? So if I have minus supply, then the DC voltage at this point is 0. And this will be minus VCC. And if this is 0 and the load is connected to ground, I don't need this decoupling cap, because the DC is already 0. Okay? And therefore, I don't need the decoupling cap, because if there's no signal, there's no losses. There's no current going to the load. But in a single supply, then this is half VCC. And if this is ground, I need this decoupling cap to decouple the DC. Okay? Because otherwise I will lose current even without signal. Okay? So that's the reason for that.
Fake. Exactly as we are seeing store. So now the KC, you know KC5 is like fucking shit.
Okay, so the purpose of the amplifier is because we want to drive the load, which is 32 ohm, and the op-amp is not able to do it because the maximum output current of the op-amp is only I think about 10 to 15 milliampere, which is not enough to drive this this load of 32 to the string that we want. Okay, so that's why we need this amplifier. So now how do we do this amplifier? How do we go about biasing this? You can see that there's a biasing resistor here. There is an emitter resistor here. How do we decide what are the values here? So let's take a look at this. So if this is this is minus VCC and this is VCC, then the DC voltage of VE, I want it to be 0. Okay? Even though I have this decoupling cap. Why is it so? Because the values that I'm selecting for the resistor come from standard value resistor. Standard value resistor is not something that I can craft the value that I want. Okay? The values that come from standard values are like 10K, 15K, 27K, 33K, 47K. all the numbers
Try to
that
the more increase.
are preset and you cannot select it and it's plus minus 5%. Alright? So in this case, if I want this to
I
be
never- I
half
don't think so.
VCC, sorry. If I want
Actually, I
this
did
to be
record
half
the
VCC,
benchmark.
this is a
Just on
PMP.
recording.
So if this is half
But the
VCC,
recording was the first
then this
5
voltage
minutes.
will be
You
about
cannot see the screen, yeah. He
0.7
never shared the
volt
screen.
lower than half
Only after he
VCC.
5 minutes. But
Correct?
share, yeah.
Roughly 0.7 volt below half VCC.
Then he just talking.
So that means to say,
Yeah, but he got
if
right
this
on the-
is
other
0,
screen.
then this will be minus
You cannot see the
0.7.
recording.
Okay?
But
If
my-
this is minus 2, for instance, this is minus 0.7, I would have 1.3 volt on this side, and probably 2.3 volt, what did I say? 1.3 volt, then this will be about 2.7 volt across this resistor. Right? And therefore you can select two resistors so that you get about 2.7 volt here, 1.3 volt here. Okay? With this 1.3 volt, you up 0.7, you will be having about 0 volt, right? If this is minus 1.3 volt, you up 0.7, you will get about 0 volt. So that's the idea behind it. But we have not considered beta. Right? So what would happen to beta? Whatever current here, okay, divided by 1 plus beta is the base current. Why 1 plus beta? Do you remember? Yes, huh? So whatever current that is at the emitter, when you divide by 1 plus beta, you get the base current, right? And this base current is going to supplement whatever current that was here. And that means the selection of this resistor may not be what we want, because we have added base current coming in. Remember, was it last week? We calculate the resistor R1, R2, RC, RE and find the power. Remember, to find the power across each component. In that particular case, there was a base current that is flowing to the Thevenin's equivalent, that is equivalent to 50 millivolt. Hello? Do you remember all this? Was it last week? Or the week before last week? No, before last week, you guys are still having Orchard Road, Jurong Point and all this. So, remember we calculate the power, we say, oh, okay, it was 15.05 volts here and 14.95 volt here, because there's a voltage drop across the Thevenin resistance, right? Same here. Right now, if you take these two resistors and parallel it, you get the Thevenin's equivalent. Okay? And therefore, half VCC through the Thevenin's equivalent will go to this point. And you would have to do the same biasing to find out the voltage at the base and so on. So therefore, what I'm trying to say is, whatever resistor you use here may not be the value that gives you 0 volt here. You may need to have a resistor in R2 that is smaller than what you expect because of this extra base current flowing. Okay? So basically that's what it is. So the purpose of it is to set the voltage here to bias this transistor so that the voltage here is roughly 0 volt if it is dual supply. Later on, when you go to the lab, okay, you will be using ground and a positive supply. Okay, so when that happens, this point will be half VDD, and that is why we need this cap. So for your assignment, okay, you may treat it during the biasing to find out the value of the resistor. You can first treat it with a single supply, right? let's take a look whether I have this here somewhere. So first, if you make use of your two battery, right? Each of them maybe let's say 1.25, 1.25, or rather 1.5, 1.5. In your assignment, I guess you'll be using 2 point something, all right? And therefore you would have whatever voltage here times 2 because with respect to ground, okay? And you want this point to be half the supply. So the purpose of having this being half the supply is because you want the swing at the output VE to give you a swing that can swing both sides towards VDD or VCC or towards 2 VCC and the other end towards ground. Alright? And therefore you need to bias this at half VCC for that, or rather at VCC because this is 2 VCC. So if this is VCC, this is ground, this is 2 VCC, then the voltage swing at the output, if it is AC, is able to swing both ways, towards VCC and towards ground. Sorry, towards 2 VCC and towards ground. Okay, so that's the idea behind it. So for the biasing, okay, you would choose 2 resistor. All right, if you go and choose, let's say you choose 20K, then this will be VCC, correct? But it is not, because there's base current going in. That caused this voltage to be lower than half, or rather lower than VCC because of the base current. Okay, but you would want to use 20K because you have this voltage drop across the VBE. That means to say if this is VCC, because this is 2 VCC, if this is VCC, then the voltage here will be VCC plus VBE. Right? So the voltage here has to be higher. And therefore this resistor has to be higher than this resistor. So R2 has to be greater than R1. Okay? And you need to select it such that the voltage here is about 1 VBE higher than half VCC, or rather VCC. I've been confusing myself with half VCC and VCC. So if that is 2 VCC, of course VE is 1 VCC. Okay? Okay, so then you can select the values here. For instance,
Yeah, bro. It's not so not bad. You buy the fixed stuff.
How do you deliver?
Oh, just ship.
Ship to your house already?
Yeah.
Because last time need to have like third party.
Oh yeah. Now okay.
No, okay.
Yeah. My friend all always buy. Some half.
what shall we use? Let's say 13K.
They can sell fixed stuff for the
I want to try the fixed stuff. What else you can come to? This is the 1K65 kg. I just want to try it. Oh wait, I saw that on the
Oh, what's that?
No, I said no. Oh, this one I saw on
Oh, then what was that? This app called?
AliExpress.
Oh,
Shopee still the best. I buy on Shopee. Yeah, bro. I always use Shopee.
But your electronic, you never use Shopee.
But use Shopee buy.
The AirPods all this.
The AirPods, I buy Shopee there. AirPods, the headphone. I buy 600. I buy more than 2
So as you can see, if you look at this
$20
dot operation point, okay, we are not doing too well, okay, because the base voltage is 1.9 volt, okay, and the emitter voltage is 1.18.
Yeah, but it's refurbished. I
Okay.
think it's a brand new one.
Okay. That is alright.
Both.
Okay.
Okay.
So yes, you can
6 months old.
roughly do this, but this voltage is too low. We want this voltage to be at 2 volt, right? So that means to say the base current that is flowing in through here is too high, right? And we have no choice, because if we don't make this, if we don't make the current at the output high, then looking into the emitter you have 1 over GM. Remember, the output impedance looking to the emitter is what? Is roughly 1 over GM, right? And that value is small, and therefore there's a potential divider between this and this resistor. If the potential divider between 1 over GM looking into the emitter and this emitter resistor is too unproportionate, then the amount of signal loss from the base to the emitter is very high. Okay, so we need to make sure that the resistor here is of sufficient value as well. At the same time, because there's a base current flowing, that causes the voltage here to be lower. Okay, due to the fact that the base current will flow from the top into the base. Okay, so we may have to choose a value that is different. All right, instead of 13, maybe we have to make it even higher. Right? Smaller. Let's make this, for instance, 10. Of course, we are not supposed to do this. You're supposed to do some calculation based on this part number. You go in and take a look at the part number. I don't have the spec for this. If you look at the part number NN2N3904, there will be a beta curve, right? And the beta curve will depend on the collector current. So you can choose at what collector current, what beta, and because of that beta, what base current is going through, and therefore determine the base current that's flowing in here. Okay, and that will determine what sort of resistor you should have it. This is still no good. So that means because of the current being so large, right, we may need to use a resistor at this point that is much smaller. Is the aircon working?
Yeah.
Huh?
Yeah. Okay.
You feel it?
Yeah, I feel it.
Okay. So we have to make sure we get the voltage here to be about 2 volt. Okay. So increase the resistor, or rather, decrease the resistor here, or increase the resistor at the bottom side. Okay, to do that. Okay. The same thing goes for if you use the
I'll give myself a
Okay, you could also do the case for the PNP. In this case, you want this voltage to be at, for instance, 4 volt here, 0 volt here, then this will be 2 volt. And if this is 2 volt, this will be about 1.4 volt, 1.3 volt. Okay? But because if this current is large, this voltage may not be 0.7 volt, maybe 0.8 volt. Right? So if this 2 volt is 1.2 volt,
But you got
you
do the
would want this resistor to be smaller compared to this, so that the voltage here is going to be about 1.2 volt with respect to 4 volt on the
Also,
top.
just do the
Okay? Just biasing this this amplifier. Okay? And then when you do have together with the op amp, all right, then you're going to drive a load that is 32 ohm, right? So this means that when this guy swings, let's say you have 4 volt, right? Then this swing will be about 2 volt, right? So 2 volt divided by 32 ohm is going to be the DC, the swing current that is flowing through this resistor, and that is in tens of milliampere, right? And therefore, this transistor must be able to deliver this current plus the biasing current, okay? So the two current together may add up to be in the region of, let's say, 50 milliamp, okay? So it's quite large, and therefore the voltage drop across this base emitter is going to be about higher than 0.7, 0.8, or even 0.9 volt. And that causes the voltage here to be higher than half the supply by about 0.9 volt or 0.8 to 0.9 volt, right? And therefore the two resistor here is not going to be the same, okay? R1 would become smaller than R2 sufficiently, okay?
Oh my gosh,
So again, you do your normal DC analysis by first finding out the Thevenin's equivalent, okay? Thevenin's equivalent of these two resistors, okay? And then you can again do the the loop equation. You say the voltage V equivalent, okay, is equal to IB times R equivalent, okay, plus VBE plus the voltage drop across this resistor, so that you can get the base current, right? From the base current, you can find out the collector current and so on. So you do a normal analysis to find the DC operating point, okay? And this part is from your experiment 1 or assignment 1, right? No change to that. Any question? Has the assignment been uploaded?
Yeah.
How's the assignment? I didn't get to see. By the way, same as last year. That's JJ. So it's quite usual to see question 3 in the exam based on your assignment. Similar to your assignment. So yeah, so it could be with capacitor, right, to find out the frequency response. I haven't seen it yet, I don't know. But it could be, because if you look at the past exam paper, it has always been that way. is either it links to the amplifier with all the capacitors. Remember right now when we're doing tutorial 7, the capacitor that we use is infinite, alright? But when it comes to exam, that capacitor would have a value because it's linked to frequency response, where JJ will be teaching you all. Okay? So yeah, so pay attention to some of these things, and when you're running the experiment, you will get to find out all this. So, can you tell me what's the purpose of C1 or CI? CI has the same function as CC. It decouples the DC here from the output of the op-amp to the input of the power amplifier, because otherwise the DC voltage will go through the amplification, and therefore the output will either be stuck at VCC or ground, depending on the voltage. Is it negative or positive? Right? So we don't want to allow the DC voltage to enter, so we decouple the DC. Only allow the AC to flow through. Okay, so if the AC flow through is fine, right? It will not go and modify the DC condition into this amplifier. Okay, so C1 CI here is again a AC coupling capacitor or DC decoupling. What about CL here? CL here is to limit the bandwidth, okay? To limit the noise that would enter the amplifier. Because by having this capacitor, a big part of the noise that is outside the audio band will be shunned to ground. Okay? We don't want this noise to be amplified, right? So we shun it to ground. We only allow the audio signal to pass through. So the frequency that allow to pass through is the audio signal that is coming from your heartbeat, low frequency, alright, that pass through. So any frequency higher than that gets shunned to ground. Okay? Any frequency that is sufficiently low enough but higher than DC gets coupled through to the amplifier. Okay, so that's basically what it is. Any question before we move on to tutorial 7? Am I right? What is tutorial 7? MOSFET. Any question? Now let me take a look at. Oh, I think I have the assignment, right? The assignment. This one. Yeah. So all this just to tell you that the voltage across this load, okay, in DC should be 0. Okay, we don't want to have any DC voltage across this. We only want the AC voltage to go across the load. Okay. Yeah. So this is where it is. Let's take a look at. Okay. So this is the specs for the transistor. Given all the breakdown voltage across the base to collector, base to emitter, and so on. Let's see the beta curve. Reverse bias, collector current, charge. What is this? Oh, rise and fall. Output emitted current gain. Okay, so this is beta. Okay, HFE. If you look at this, okay, current gain HFE is beta, right? So if you look at beta, a quick check. No, cannot. So given here, beta is about 150. Okay, 150, depending on the current. So if the current is 3 milli, how much is it, and so on. 10 milli, it is still 100. Okay, and so on. So you can make use of this beta curve to find out what sort of base current would be at the base, because if the collected current is 10 milli, so if it is a beta of 100, you are at 100 micro flowing through the base. But right now this beta is more than 150, so the base current will be smaller, and so on. So you can make use of this to roughly determine the kind of current that is at the base. Okay. This is when the current is a lot bigger. Look at this. So this is normalized to, I think, 100. So you can see that when the current start to increase more and more, collected current start to increase, the beta start to drop. Okay, so depending on the current at the output, the beta can be much lower. Okay. Yeah, so basically this is what it is. So you can look at all this. If you look at the PNP, it will be not as good as well, I think. Okay. Okay, so there is the PNP. Again, you can see the beta curve. Okay, so there is the beta curve. Then we look at the high current. Your beta is dropping at the higher, near the higher end. The beta starts to drop a lot more than when it is at lower collected current. Okay, so you have to find out all this when you are estimating what sort of value you want to use. Okay, any question before I move on?
When is the next semester? When is the next semester?
11 week 11.
11.
Saturday. April.
2nd November.
Second of I don't know the exact. I know week 11.
When is the clash or makeup?
I mean I probably won't go that shit.
Go makeup.
No.
ML.
Keep a watch for this,
Makeup I won't skip.
because when it comes to frequency response, this will become part of the deal in finding out what sort of capacitor to use and all this, right? So follow this and find out. So here you have the RCR. So this two resistor and this C together makes an RC. Alright? So the value of these two capacitors will be summed together and multiplied by the C to give you the time constant required here. Similarly here, these two resistors add up together with this resistor form an RC that will determine the frequency that would be allowed to flow through this capacitor, same as this, right? So here they want you, or you are required to find out the impedance for frequency higher than 20 Hertz, because we want to hear signal that is audio that is above 20 hertz, right? And therefore that's why you want to find out the impedance of that capacitor where it is higher than 20 hertz and so on. Yeah, so these are some of the things that you need to be aware of. Okay, so coming in, you have a simulation of 2 microampere that is coming from this microphone, AC that is being coupled in, okay, and then goes through your amplifier, which act as a preamp, and the output here drives the power amp, right? So this is what you're going to do for the experiment next week, right? Is it next week? Is our experiment next week? Or the week after next? It's not this week. I don't remember if this week. I think it's next week.
What thing next week?
No, sorry. It's after the assignment hand in. So it's 2 weeks from now.
Okay, about.
Okay.
Oh, we need to submit these 2 weeks.
Subsequent.
Yeah.
Any questions?
Like this after you submit. It's like it will be like that.
Yeah. We submit the next week.
If no, then let's move on to the tutorial. Okay. I briefed you all on the MOSFET already, right? Did I introduce enough? I did? I did? Okay. Anyway. Let me give a quick one. So MOSFET. 2 atas. Okay, MOSFET stand for metal oxide semiconductor field effect transistor. Okay, basically symbolically it is drawn this way. Okay, so this is the PMOS and this is the NMOS. The symbol varies a lot, but wherever you see the arrowhead, it tells you that that is the source. Okay, so this would be the source for the PMOS, this would be the source for the NMOS. And this symbol for different book can be quite different. Some may have dotted line and okay, to indicate that the channel is not always complete. Okay, sorry, NMOS would be over here. Right? And in digital design, you may just see a transistor without arrow. Okay, for the PMOS, there will be a bubble. Okay, so whether it is any one of this, it is still PMOS. Whether it is any one of this, it is still NMOS without the arrow. Okay, it means that for a given transistor, for instance, NMOS transistor, it would be some polysilicon gate that separate the source and drain. Okay, so sitting on the P substrate. Okay, and therefore when you apply voltage at the gate, the polysilicon gate, it will attract the negative carrier to the surface, forming a channel. Okay, and once the channel is formed, if you apply a voltage between the drain and the source, current will start to flow from the drain to the source. Okay, the higher the voltage you apply at the gate, the thicker will be the channel, allowing more current to flow because the resistance becomes smaller. Right? The more voltage you apply to the gate, the channel resistance becomes smaller, more current will flow, and therefore the equation that governs this is ID, the current at the drain, which is also the same as the current at the source, because there is no gate current. Okay, there's no gate current, and because of there's no gate current, the drain and source current are the same, and is given by the equation K prime over 2 W over L into VGS minus VTH square into 1 plus lambda VDS. Okay, so this is your saturation equation. There is another equation which is known as the triode equation, and that equation, same thing, ID will be equal to IS is equal to K prime without the 2 W over L into VGS minus VTN, if this is NMOS, okay, minus half VDS multiplied by VDS. Okay, so this is the triode equation. So triode equation is meant for digital circuit. Okay, for analog, we will insist on using the saturation equation. Okay, and if you take a look at this equation, okay, and you vary the VDS, you will end up with this curve. And for different VGS, you have different curve. So when VGS increase, you have a family of curve. And all this curve, when you project it to the negative real axis, it will all intersect at one point, and it is lambda, the channel length modulation term, which appears here. Okay, and to find out, so when the transistor is operating in the triode region, it is on the left side of this dotted line. When the transistor is operating in saturation region, it is on the right side of this dotted line. Okay, and why is there a difference when you are operating in triode and saturation? Is because when you increase the voltage between the drain and source, the depletion region here start to push this channel, and the channel got deformed, and it becomes this. And this channel is discontinued here, and this is known as a pinch-off region. Sorry. It is a pinch-off region. So during this region, the current that flows through from this edge to the drain is going through what we call saturation velocity. Okay? And when that happens, you have this point here, or this line here. So as we increase the drain voltage, this channel gets pushed further and further away, okay, and this slope gets to move in this direction, okay, and we're going to make use of this transistor as an AC device, and it will end up having this AC model. And this is your gate, your drain, and your source. And between the drain and source, we have the output resistance R0, and the current source that control this device is a voltage control voltage source. A voltage control current source. Okay, this is a current source, and this current is GM VGS, where VGS, the voltage, the AC voltage between the gate and source, would control this current and would give you the drain current that you need, that is flowing through this. Right? So because of this, you need to go and find out GM, you need to find out R0 from the operating point. So if you take this, you go and do a DC analysis, you would go and find out the DC operating point, and this DC operating point will give you ID and VDS, and from ID and VDS you can find out R0, the output resistance, which is equal to VDS plus 1 over lambda divided by ID. Okay, both of which come from the DC operating point. Okay, you can also find out the GM of the transistor. Okay, GM is known as the conductance of the transistor, which is basically delta ID over delta VDS. VGS. Okay, so if you look at this, you can take a look at this equation, okay, and you can then differentiate this equation with respect to VGS, and you will get the GM. So for convenience, to simplify things, we will make 1 plus lambda VDS equal to 1, and we differentiate this. When we differentiate this, we will end up with K prime W over L into VGS minus VTN. Okay, and that is the equation for GM, which we can then make use of it to calculate GM if we know VGS. All right. However, we can substitute this equation back into this derivation here to find out the different form of GM, and it can come as 2ID over VGS minus VTN, or root of 2ID K W over L. Okay, so it can come in all this form by substituting this equation back into here. Right? And you will see that this three form, okay, if you don't have the current, you need the VGS. If you don't have the VGS, you can use this equation here. So depending on what you don't have, you choose which equation to use. Okay? And once you have these two, you already will be able to find out the AC equivalent to this transistor, and therefore you can replace the transistor with the AC equivalent so that you can evaluate the gain and output impedance and so on. Okay? Any question? The same thing would be for PMOS. You could do the same for PMOS, except that PMOS, the current flow from source to drain, whereas NMOS flow from drain to source, right? which both case the gate current is 0. Okay, so once you know this, you can proceed in doing your tutorial. So the triode, when the transistor is in triode, okay, VDS is smaller than VGS minus VTN. When the transistor is in saturation, okay, VDS must be greater or equal to VGS minus VTN. Okay, so these are the two things that you need to know in order to know whether the transistor is in saturation or in triode. Okay, and because we want the transistor to operate in saturation, then of course when you design anything, you must make sure that the transistor is in saturation so that the gain can be made high. Okay, in triode the gain is very low.
Sorry?
Okay.
You just don't know the convolution.
All right. Now let's take a look at
Oh, this is
tutorial 7.
until the
So in tutorial 7, you see question 1. Okay, A and B, and there's these two circuits. So let's take a look at these two circuits.
Oh no, I just read the lecture. I just read the lecture notes. For diode, right? I just read additional. Yeah, I just read small thing. Yes.
So given to you that the
Sorry.
Kn is 0.5 milliampere per volt.
This one is the 2000.
Oh, this
Okay,
one. Oh, this one. This is the
and,
practice. Just
and
read.
the threshold voltage
I haven't start.
is 1 volt.
Start part 2 already.
So how do we go about looking into this? So if you look at this, you can do this loop. Okay. So in this loop, Ig is 0. There's no Ig. So this resistor of 1 mech connected to ground is not relevant at all. The voltage at the gate is 0 volt. Okay. Therefore, what we have is that we have VGS, okay, plus ID times the resistor here, that is 3K, is equal to 15 volt. Okay? We can assume that the transistor is in saturation because you need to either assume one case or the other. So if we assume that the transistor is in saturation, then we can write the entire equation in ID or in VGS by making use of the equation ID is equal to K,
That's the fourth one.
okay, over 2
Fourth one.
VGS plus minus VTN square. Okay. Right now, this is Kn. It is the equation just now I wrote is with the prime. So when we put the prime, W over L has to be included. Without the prime, okay, W over L is already included in this Kn. Alright? So now, based on this, you can substitute this term into this equation, and therefore you have VGS plus, instead of ID, you can write K over 2 into VGS minus VTN square times 3K equal to 15 volt. So you end up with this equation. And with this equation, you can expand it to get your equation in VGS. Okay? Or you can substitute VGS instead of VGS, you can replace it with ID, and if that's the case, you end up with instead of VGS, you can write this as root of 2ID divided by K, okay, and then you plus VTN, and this would be VGS. Using this equation, right, bring the 2 over, bring the K below, square root it, bring VTN over, plus VTN, this will become VGS. Okay, VGS plus ID 3K is equal to 15 volt. So you can either expand it in ID or expand it in VGS. Right? In both cases, you will end up with a quadratic equation in ID or in VGS, and therefore you have to solve the quadratic equation to find out ID or VGS. So if we use this equation, then we can expand it, and we will end up with ID squared minus 9.78 ID, okay, plus 21.78 equal to 0, okay, by expanding this, okay, substituting this for 1 volt, okay, substituting this K for 0.5 milli, you will end up with this equation, okay. After you've gotten this equation, you can use your x, or rather the value of x is equal to minus b plus minus root of b squared minus 4ac over 2a, alright, and you can now go and evaluate the value of ID. You'll find that ID is equal to 6.35 or 3.43 milliampere. Okay, it's either one of these values because of the plus and minus. Okay, and if you use ID equal to 6.35, then VGS becomes 15 minus 3.3 times 6.35, and that will give you minus 4.05. Okay. 3, because 3 is in K, this is in milli, so K and milli cancel off, so we don't need to write the K and the milli here, and you end up with this value. Okay. If you look at this, VGS has to be a positive value, you end up with a negative, so this is a no-no. So we find the other values here. If you put ID is equal to 3.43 milli, okay, then what you will get is VGS is equal to 15 minus 3 times 3.43, and that works out to be 4.71 volt. Now this is positive value, it looks okay, and on top of it, we know that VDS must be greater or equal to VGS minus VTN, right? So VDS is 4.71, okay? VGS is equal to VGS is equal to this, VDS, VDS, so we have to find out VDS. VDS will be equal to VDD, okay? VDD minus this drop, the remaining will be across the drain to source, right? So VDD minus VDD minus VDD. That's the two supply. Okay. Minus ID times 1K minus the same ID times 3K, and therefore you find that the voltage across this is 16.28 volt. So in order to find out whether the transistor is in saturation, you want VDS to be greater or equal to VGS minus VTN. So this is 16.28. Is it greater than 4.71 minus 1? Yes. Therefore it implies that the transistor is in saturation. Okay? So that's how we evaluate part A. Okay?
For this question,
Let's look at part B.
this is what they give. You mean why is it? What is different?
In 1B,
This for this.
you have this circuit here,
This is the
okay,
X2.
which is basically this.
This is for conversion.
Sorry, 1.6K. Alright, we are given that for the PMOS, the VTP is 1 volt, okay, and the KP is 250 micro volt
Then this one is no longer
sorry, micro ampere per volt.
This one.
Okay,
For correlation. So yeah, conversion is for continuous.
so based on this, again the same thing. You can write the equations. We know that
Sorry,
VSG of this transistor is 4 volt
N minus. But this one is N plus
because
for
the source is on the positive plate,
Costa. That's the only difference.
the gate is connected to the negative plate. So VSG is 4 volt. So if you write the equation ID is equal to KP over 2 into VSG minus 1 volt square, okay,
Autocorrelation.
then this equation will
Then
give
right,
you
your N plus N
KP,
is stuck.
which is
The
250
zero is minus N.
micro over 2 into 4 minus 1 square.
Autocorrelation.
Okay, this gives you 125 micro times 3 square, 9. Okay, and if you work this out, the voltage, the current that you are getting is
The next one, right, is the same thing, but then you
1
first
point.
pointer, 0, starts from minus.
Yeah, sorry, this is 0.
That's the only difference.
So this will be equal to 1.125 milliampere.
Yeah, then yeah.
Okay.
Pricing.
So based on this,
So
we can find out VDS.
spend like 1 hour.
This is, we are assuming that the transistor is in saturation. So to find out
But
VSD,
this only for all.
VSD will be equal to the voltage here, which is 4 volt,
Yeah.
minus the voltage
I
drop
just don't know, but I just remember it starts with minus.
ID times 1.6K.
Then
Okay? And that works out to be 4 volt minus 1.6 times 1.125. That works out to be 2.2 volt. Okay? So we need to find out whether VDS is it greater or equal to VSG minus VTP.
Because I read some also.
So if we look at this, this is 2.2 volt. Is it greater than the voltage that is 4 volt
Actually makes sense.
minus 1? No.
N goes to 2.
So therefore this implies that the transistor is in triode. Okay. Okay. Because 3 volts is definitely greater than 2.2.
I just remember.
Sorry, what's this graph?
This is the this one. This one, the X.
Actually, it doesn't matter, right?
Any question?
Like, we never even use it.
Actually, but we're gonna do auto correction using. If you want to do the capital.
Actually, as in, if I say,
No, we only cover one question.
same.
Same.
So if I just use this one, shift to plus or minus 7, which is so I know that is to I straight away why do I need to
Any questions?
This is the notation for the second graph. And also because the final one, right, is based on n. The final graph n actually.
Where's the attendance list?
That's why you use n.
Who hasn't marked attendance?
I don't understand why I would need to write this.
I don't understand why. Like, as you need to write this.
Because I can derive all this from this one. If I know that I correlate this graph,
I mean, you can't draw manually. But actually, I think if you can get also okay. But then I'm not sure about the working mark. They want you to draw. I don't know if you get.
right? This one, the working mark I can get from this one. I won't ever need.
Oh, like you won't ever need to draw this part. Oh yeah, I will just start from here straight away. Just to show.
So my this
This one is just how you draw it.
theoretical.
Yes, it's attempted lah. It's not how you draw this one. This one, right? This one you get this.
So is it like every time, as long as it's auto correlation, you just need to
It's okay. Just like
Draw. This is the template lah, but you can just start.
no. As long as
You
you
just need like
I can't remember this.
then it's okay. Then you can why?
Just remember this one, right?
Okay.
But if it's different graphs, then it's not, it's just correlation.
Oh, that one is cross correlation.
But there's different properties, right?
Yeah, cross correlation. The phase doesn't matter.
But
Anyone
you
else?
get the final answer the same.
Yeah, same. Yeah, just
So align to once it's not intercepting, then find out then continue.
yeah. Then you get.
You all managed to buy and claim the what call it? EIP.
You never use it.
Yeah, use bro.
The claim.
Oh, the claim. Ours, the one we are getting is not claimable. Or not claimable. No, no, why?
For the claim, then they claim.
That's not claim.